Okay, so we're still talking about limits at infinity, and now we're going to look at some more meatier examples than the ones we looked at in the previous video. So the thing that we want to be careful of is, once again, indeterminate form. We've looked at before how if we have 0 over 0, it's meaningless to us. We call it indeterminate form. The same is going to be true if we have infinity over infinity. So I'm going to kind of come back to that little asterisk there in red, and I'm just going to try to take the limit on number 1. So if I think about using direct substitution, I would have 2 times infinity, which is going to just be a huge number. So even though I take 1 away, I'm still going to have a huge number. So I can assume that that means that I have infinity on top. And then same thing at the bottom. So if I have a really big number and I add 1 to it, I still have a really big number. So notice I have this indeterminate form. So what I can do is I can divide every single term by my largest powered x value. So that's kind of taking this idea right here, and you'll see why in a moment. So right now I have x to the 1 on top and I have x to the 1 on bottom. So x to the 1 is my largest x value. So I'm going to go ahead and I'm going to rewrite this example or this problem as the limit as x approaches infinity of 2 to the x over x minus 1 over x all over x plus 1 over x. I'm not breaking any math rules because I can do the same thing on a fraction to top and bottom as long as I do it to all my terms. This then reduces to be the limit as x approaches infinity of 2 minus 1 over x all over 1 plus 1 over x. Now notice that when I do direct substitution, according to that theorem that we looked at in the first video, 1 over infinity is going to approach 0. So on each of these, so I'm going to have, so 2 is going to remain 2 regardless of how big we get. 2 minus 0 over 1 plus 0. Well, that's just going to give me 2 over 1. So my answer to my first example is going to just be 2. I'm going to do the same thing for my second example. Notice when I try doing direct substitution, I am going to have 2 times a huge number plus 5, still a huge number, so infinity. 3 times a huge number squared, still a huge number, plus 1. So again, I'm going to have infinity over infinity, so I notice that that's going to be that indeterminate form. So I'm going to go ahead and instead divide everything by my largest powered x value. Well, I have x to the 1 and x to the 2. X to the 2 will be my largest, so I'm going to rewrite this as the limit as x approaches infinity of 2x over x squared plus 5 over x squared all over 3x squared over x squared plus 1 over x squared. I'm going to clean that up by simplifying a little bit, and I'll have the limit as x approaches infinity, so of 2 over x plus 5 over x squared, all over 3 plus 1 over x squared. Well, again, using that theorem from the last video, I'm going to have using direct substitution, 2 over infinity is going to drive towards 0. 5 over infinity squared is going to drive towards 0, so I'll have 0 plus 0 over 3, again, 1 over infinity squared, 3 plus 0. Well, that's going to be 0 over 3. I know that 0 over 3 is just the same thing as 0. So on my second example, I get a limit of 0. Looking at 2 more examples of this type, just to see kind of all the different possibilities I can get. On example 3, again, I try direct substitution. Direct substitution is going to give me infinity over infinity again, so I'm going to divide by my highest powered variable, which is x squared. So I'll have the limit as x approaches infinity of 2x squared over x squared plus 5 over x squared all over 3x squared over x squared plus 1 over x squared. Even if you feel like you understand this now, please do make sure that you continue watching because I need you to be able to see how to do limits with radicals and limits with trig functions. I plug infinity in. I see that my first term will drive towards 0. My second term will drive towards 0. No, I'm sorry. My first term will drive, first I'll reduce. Let me back up. So I get the limit as x approaches infinity of 2 plus 5 over x squared all over 3 plus 1 over x squared. So my first term will remain 2. My second term will drive towards 0. On the bottom, my first term remains 3. My second term drives towards 0, and I do get 2 over 3. And looking one more example of this nature, I'm going to go ahead and doesn't matter if it's negative or positive infinity. I try plugging infinity in or negative infinity in. It doesn't matter. I notice if I plug negative infinity in, I end up with negative infinity over positive infinity. So again, a form of indeterminate. So I'm going to go ahead and divide by x cubed, and I'll have the limit as x approaches negative infinity of 2x cubed over x cubed plus 5 over x cubed, 3x squared over x cubed plus 1 over x cubed. Cleaning that up a bit, I get the limit as x approaches negative infinity of 2 plus 5 over x cubed all over 3 over x plus 1 over x cubed. I notice that that's going to stay a 2 on top plus 0. And on the bottom, I'm going to get it 0 plus 0. Well, I know it's not okay to have 0 on the bottom, so I know that this is going to be undefined. And if you look at the graph of this using, say, a graphing calculator, you're going to see that the reason it's undefined is because I'm going to be approaching negative infinity. It's going to continue, the graph will continue to go down and down, so decrease without bound. Therefore, my limit does not exist for that reason on this one. All right, so now let's move on and look at limits with radicals. The same rules will apply. We just have to look at determining what our largest powered variable is a little bit differently. So if I look here, an example, the first example with radicals, I notice that on top I have an x, and on the bottom I have an x squared, but the x squared is under a radical. So technically I have the square root of x squared, which notice reduces to x. So in this particular instance, I'm going to go ahead and divide everything by x. So rewriting this, I get the limit as x approaches infinity of 3x over x minus 2 over x all over, I still need the radical, so now I'm going to have 2x squared. So notice because it's under the radical, just like I pointed out over here, I'm going to have to put it as x squared, which because under the radical it is technically an x. So over x squared minus 1, still under the radical, so it's still got to be an x squared here. So now from here this becomes the limit as x approaches infinity of 3 minus 2 over x all over the square root of 2 minus 1 over x squared. Using my direct substitution, 3 remains a 3. 2 over large numbers, 2 over infinity will be 0 over the square root of 2 minus 0, giving me 3 over the square root of 2. Or if I wanted to, 3 times the square root of 2 over 2 if I rationalize that denominator. Looking at another example with radicals, I'm going to do the same thing. So first thing I'm going to notice is I have an x variable on top, and on the bottom I have a square root of x cubed, which I know is the same thing as x to the 3 over 2. Well, that's going to be my highest powered variable, so that's what I'm going to have to divide everything by. So I'll have the limit as x approaches infinity of 3x over x to the 3 over 2 minus 2 over x to the 3 over 2 all over the square root of 2x cubed. I can write that as x cubed because it's under the radical, which is implying that it is x to the 3 over 2 plus 1 over x cubed. Doing some simplifying, I get the limit as x approaches infinity of, so if I take an x out of both x and x to the 3 over 2, I'm left with x to the 1/2 on the bottom minus 2 over x to the 3 over 2 over 2 all over the square root of 2 plus 1 over x cubed. I plug infinity in. On the top I get 3 divided by the square root of a huge number is still going to be 3 divided by a huge number, so I'll get 0 minus 0 all over the square root of 2 plus 0, which is going to give me 0 over the square root of 2, which I know is going to reduce to 0. Looking at one more topic, with trig functions, we need to know that if we're looking at the sine and the cosine trig function, if I were to look at the graph of sine, I know that sine starts at 0 and then is this wave function. So notice that the sign as I approach infinity is just going to continue to oscillate back and forth between 1 and -1. Notice cosine starts at 1 but kind of does the same thing. So for that reason, if I'm looking at the limit of sine or cosine as I approach infinity, neither of them exist. However, if I look at the limit as x approaches, and this is supposed to be infinity, not 0, so I'm going to change that, of sine of x over x, that is going to be 0, and let me show you why. So if you remember the squeeze function from when we talked about limits before, I'm going to use that. So first thing I'm going to say is I know that sine of x is in between -1 and 1. It oscillates back and forth. I know I can do the same thing to all three pieces of an inequality, so I can divide all three pieces by x, and I'm assuming x isn't 0 because x is going to be approaching infinity. If I then took the limit as x approached infinity of each piece, the limit as x approaches infinity of -1 over x is going to be -1 divided by huge numbers, which will drive to 0. I don't know what sine of x over x is. That's what I'm trying to prove. If I take the limit, and let me erase that because that's what I want to, oh, nope, I want to keep that. If I take the limit as x approaches infinity of 1 over x, I'll have 1 divided by huge numbers, which I know is going to be 0. So that is where this comes from. So when you're looking at trig functions, remember to kind of think outside the box a little bit and use some of those rules and some of those formulas that you learned back in the previous chapter with trigonometric functions and limits.